So welcome to AstroTours. If this is your first time coming out, welcome. We hope you enjoy the night. If this is your second or third or even more time being here, we're glad to see you back. If you're not familiar with AstroTours, we usually have our events on the first Thursday of the month. And so this is something that is run, sort of organized by the graduate students in the Astronomy and Astrophysics department here at the University of Toronto. And we also have tremendous help from volunteers, other students who are in astronomy, physics, and aerospace here at the university. So we really value the feedback that we get. We've switched away from the paper forms and we've moved on to online feedback. And so you can find that we have signs posted around, but it's bit.ly/AstroTours. So if you know where you are, you should be able to find the feedback form. But we also have some signs around to just do that short survey. And if you can show us the, on your phone or whatever that you filled it out, we have cookies as usual to try and incentivize you to provide your feedback if the warm feeling of helping us out isn't sufficient. After our talk tonight, normally we do telescope observing, but I'm pretty sure it will unfortunately be too cloudy to observing tonight. We will still have one of our domes open to be able to have one of our volunteers showing the telescope. We won't be able to look through it if it's cloudy, but just be able to see one of our telescopes, and you can ask questions and hear about how telescopes work. We also have Planetarium Shows, so there were some tickets being handed out for those Planetarium Shows as you came in the room. I believe there's still some available, so we'll talk more about that after the talk if you would like to get a ticket for a Planetarium Show. We also have free snacks, an Oculus Rift, and some other demos, so please do stick around after the talk for some more activities. Our speaker tonight is Dongzi Li. She is a PhD student here in physics and also at the Canadian Institute for Theoretical Astrophysics. She is an expert on pulsars and uses their light to study and understand structure and material in our galaxy itself. So let's all please give Dongzi a warm welcome.
Hi everyone, so I'm Dongzi, and today I'm going to talk about pulsars, which in my opinion is a really, really cool object, and I wish you will agree with me after the talk. So I'll start with what is a pulsar. So after years of study, now we have a relatively good idea about that. But this is not how we astronomers tell a story. We always start from what has been observed. And then just like the detection movies, we step through all the observational clues and we make guesses, and finally you have some relatively nice model, and then we can tell the coherent story. So what is a pulsar? Pulsar was first observed in radio. So now I have to explain what is radio. This is the visible light we can see with our eyes. However, it's actually a pretty narrow thing, and for astronomers, we are taking advantages of light of far more wide ranges, from wavelengths of atom size to wavelengths of mountains. This is a little bit exaggerated, actually. Most of our radio astronomers working on sizes of humans, so like meter wave. And to make you more familiar with the word radio, well, you'll think about radio. And this is true because radio always receives signals in radio band. And also more familiar, cell phones. We're using radio waves to send and receive cell phone signals. Actually, the first radio, astronomical radio signal is received when Bell Telephone Company is trying to debug their transatlantic service. And they find some weird noise and they couldn't distinguish what that come from. And so they hired a very talented engineer who is Jansky, and he found that actually that is from the galactic center, and this is the first astronomical radio source discovered. And afterwards, there are tons of radio, telescope has been built, and people started looking at the skies mostly people who is not interested in making a lot of money with the phone. And then in 1967, a grad student, Bell, discovered a mysterious signals like in the sky. And that sounds like this. Oh, can I make it louder? So you can hear the regular beep of that sound. And that later on, because there's regular pulses of that sound, so that object who emit those pulses is later on named Pulsar. And that later on comes, has won the Nobel Prize in Physics in 1974. However, what is that sound? Like, if we plot, this is time. This is the original draft from Bell. This is time, and this is intensity of that light. So you can see those regular bumps of 1.3 second period. And like I plot those like to make it more obvious, but it's actually not the same pulse. Very short, regular radio pulses of light. That sounds a little bit weird, like very regular. And also in radio band where you send and receive cell phone signals. So when that thing is first discovered, they call the thing that emits those lights LGM1, which is little green man. But yeah, that is exciting, very exciting. But later on, they have soon discovered the second pulsar, and now like there are 2,702 pulsars, and the number is increasing every day. Then the population of aliens seems to be a little bit too large, and people started to think maybe it's something more natural and with larger population. Also, the pulsar is initially discovered in radio, but then people discovered that in other band wavelengths there are similar things of same period, and that span across from gamma rays to all the way to radio. And the most amazing thing is the energy in the gamma ray is 10 trillion times, the light in gamma ray is 10 trillion times more energetic than the radio light, which means that, yeah, it's fine. If you want to contact some aliens, you can send radio waves, but you don't want to send gamma rays unless you want to blow your own planet or something. Yeah, so obviously you want something more population, and you want something more powerful and emit lots of energies. Well, the first natural gas is stars. We have lots of stars in the skies, and they're emitting light all the time, and they're energetic. And also, the stars rotates. So the very accurate periodicity can come from the rotation of the stars. Very natural gas. Actually, there's something similar effect we can see on Earth, which is the lighthouse effect. Like you can have if the light is not emitted from the whole surface of that star, but only in certain area of that stars, then once the light passes across the line of sight, you will see a. So that can explain the periodicity and the sharpness of that signal very well. However, but our sun don't pulse because it is emitting light from the whole surface. So how can you generate some light from narrow beams? Well, one of the very natural ways is to have strong magnetic field. So if you have strong magnetic field, analogy to a bar magnet, the field lines will start from the north pole to the south pole. And the magnetic field lines will constrain the motion of electrons. Oh, I was trying to draw an electron that is kidnapped, but not very successful. Yeah, but it is difficult for electrons to go transverse to the magnetic field lines. It will usually move along the field lines. So at both poles, there will be some emission because of the motion of the electrons. So that can explain the beamed light very well. So one of the things about pulsars that it has very strong magnetic field that constrain the motion of the electrons. And another weird thing about pulsar is, like the first pulsar discovered, it pulses almost 1 pulse per second. And later on, people has discovered millisecond pulsars, which means that it will emit light 1,000 times per second. This is very, very fast. Consider the Earth rotates like 1 times per day. And then there will be a huge problem. There's centrifugal forces once you rotate very fast. Just like the pizza dough. You rotate very fast, it grows large because the centrifugal force is trying to throw things away from their surface. So if the stars rotate too fast, then obviously all the mountains on the surface, all the rocks will just fall apart and throw away, and you don't want a flying, throwing stone stars. That's not stable. So we can make a very simple calculation. If you equate the gravity, like the gravity is trying to hold together the stars, and then because it's rotating, the centrifugal force is trying to make it fall apart. If you equate these two, for example, we have the Earth and we have the radius of the Earth. So in order to not let the Earth fall apart, it can rotate maximally 15 times per day. Now it rotates 1 time per day, so pretty reasonable. Like orders of magnitude calculation, it works very well. So now we start to think about the stars. If we assume that it has solar mass, which turns out to be pretty nicely worked out, solar mass, and it rotates 1,000 times per day. So what is the maximum radius it can have? 15 kilometers. What does that mean? This is our sun, and this is the Earth. Not that large one, it's that little blue dot. And this is the Earth, this is the Toronto. If I don't mark it, it's almost very difficult for me to actually find it. And then this is 10 kilometers. So it shows that I can walk from here to here in 2 hours. If I take a car, it's even faster. So this is the radius of the neutron stars. Pulsars, sorry. This is the radius of the pulsars. So you're trying to have something of the sun's mass, but you compress it to something that is as small as downtown Toronto. This is really amazing. That sounds a little bit surprising. However, this kind of object is predicted 30 years before the discovery of the pulsars. It's actually a very natural product of star evolutions. If you have it is predicted in these papers, like if you have too fast. If you have a star of mass of 7 to 20 times the solar mass, it evolves much faster than our sun. And one day, it explodes into supernova. And then it throws 90% of its material. And maybe not that much, sorry. And then compressed, falling down into a very, very, very compact core. And that is the neutron star. And the neutron star pulses, and we receive that very regular pulse signal. So now the story finishes. Like it is predicted even before we discover it. And when we discover it, all the observed thing and all our gases and measurements just matches those natural products very well. So now all of us just believe that yes, the pulsars are just neutron stars. Not so mysterious, but still very cool. So, summarize. Pulsars are fast-rotating neutron stars with very strong magnetic field. Okay, now I'm going to talk about why is pulsar so cool. So why am I interested in pulsar? That is, I'm so sincerely saying that I am interested in pulsar so that I'm working on that. First, yes, it has very extreme interior environment. Like, as I said before, it's 100 trillion times the density of the sun. You never have something so compact. It's actually the most compact object in the visible universe. When I say visible, because black hole is more compact, but you cannot see light from black holes. But pulsars is different. You can see light from pulsars. So it can help you study the things, the material structures within such a compact environment. And also, it has strong magnetic field. It is 100 million to quadrillion Gausses in the surface of the pulsar. What does that mean? The magnetic field of our Earth is around like 0.5 Gauss. So it's like at least 100 million times larger than the natural magnetic field on the Earth. And also, the strongest magnetic field ever generated on Earth is 28 million Gauss, not too far, but only lasts for 1 microsecond. And it takes 128 kilograms of some material to generate that, which is done in some Russian lab. Russians are usually very amazing at generating very amazing and weird things. Yes, so even that didn't reach the magnetic field with even the neutron star weakest magnetic field. So some of them even have quadrillion Gauss magnetic field. We sometimes call it magnetar. In those extreme conditions, what is the material like? What kind of structure they will form? Like I heard about talking about that, like inside the neutron star crust, there's some pasta thing forming, etc., etc. So it is something really amazing. It's an extreme lab that you are doing some experiment which you might not be able to do currently on the Earth. But it is doing that naturally, so you just observe it and you just know what is going on. Not yet know, but trying to know. And another exciting part about the pulsar is its extreme accuracy in period. The accuracy of some pulsars rival the atomic clock, so which is now the most accurate clock on the Earth. For example, there's one pulsar that has a period of 6 milliseconds, and the area of that period is 10 to the minus 17 seconds. So it's really accurate. Each period is just pulsed at exactly the same time. And that gives you very good timing of things. So why is that exciting? That directly leads to the first indirect evidence of gravitational waves. This is discovered when the pulsar is first discovered, it's like single pulsars. But later on, people discovered that some pulsars, the pulse is actually not so accurate. And then they find that this can be explained with a binary motion. So this is a particular system, pulsar 1913 plus 16. They have 2 neutron stars, both of roughly 1.4 solar mass. And they're in 8-hour orbit. That means like the Earth's orbit around the sun in a year. So 8-hour orbits is almost like the Earth-Moon like distance something. And both of them are the solar masses. So which means that in the orbit, there So it generates some gravitational waves in that procedure. And when this system is emitting gravitational waves, they started to orbit closer and closer because they're losing energies. So, and that can be solved with the timing of the pulses. And the orbit is around 8 hours, but the timing is so accurate that they're able to see the reduction of the orbit period by 75 millionths of a second per year, which is really a very small fraction of actually considering the 8-hour orbits. This can only be done with very accurate timing methods. And not only that, like this system, it is probing the gravitational waves and general relativity effect in its own system because it's compact and because it's closed. It also had the potential to probe gravitational waves of like other systems. This is called pulsar timing algorithms. Oh. So what is it probing? So this is one galaxy. This is another galaxy. Within each galaxy center, there are supermassive black holes. So when the galaxies are merging, the supermassive black holes is orbiting around each other, and that generates gravitational waves of like in a frequency of years or 10 years. And that can be received by the pulsar timing algorithm. So when it converges, this is two supermassive black holes. And when it is orbiting around each other, it is generating some curvature in the space-time, and that is fluctuating and emitting gravitational waves. And then that gravitational waves reaches out and oscillating and reaches the Milky Way. And the pulsar is emitting signals. However, the space between the pulsar and the Earth is modulating because the arrival of gravitational waves. So that is influencing the time the signal reaches us. So pulsar is sending out regular pulses. However, the time it takes to reach us is changing because of the gravitational waves. And if your timing is good enough, you can sense that tiny difference in that arrival times. And hence, you can actually capture some very exciting merger of galaxies in parallel universe. This is really cool because considering like 2017, the discovery of gravitational waves of LIGO, those are like merger loads, So, and the supermassive black holes are tens of millions of solar masses. Those are not like those star-like black holes merger, but much, much more massive and much, much more fierce considering the merger of galaxies. So this is great, and people have been collecting this data for 20 years, and each year they're releasing data and trying to find that signal. It's not simple because previously, when we are trying to detect gravitational wave, we are using instrument on Earth. However, if you're trying to take advantage of the pulsar first, you have to understand the pulsar very well. So it takes more years to do that. But once they discovered that, because the frequency of that gravitational wave is in the order of years, so once you see it, you'll see it for years. It's not a sharp signal, but you can study that signal, how it evolves and how that galaxy is merging, which will be very exciting. Okay. And not only this, another very exciting part about pulsar is that it's extremely compact. So it not only facilitates the natural detector of gravitational waves, but also facilitates natural interferometers, which is the largest interferometers in the world. So what is interferometers? I'll start with the light interference. So this is, I'm not sure how familiar with this. This is the double slit experiment. So you have the light from the candle, and you make it pass through a single slit, and then pass through double slit. The light from the two slits interfere with each other. So what you will see is some interference pattern of like bright, dark, because of the interference of the light coming from different paths. And you can take advantage of that because the interference pattern is telling you the path the light has gone through. So one of the applications of that is the Michelson Interferometer, where people first discovered that there's no ether in the universe. It's like you have an incoming light, you split it into two paths, and then you connect it together, and they form interference pattern. So whatever happened in the two paths, it will change the shape of the interference pattern. So this is a very sensitive way to measure tiny difference of these two light paths. And with that, the principal idea is pretty simple. But then it comes to 2017 Nobel Prize of LIGO. They just build those kind of interferometer that is like 4 kilometers long for the arms. And that is the most challenging part. They want this to be very straight because they don't want instrumentation difference of that path. They only want the astronomical difference of that path. So they build 2 arms, and the light comes from, the laser is emitting light, and they split into 2 arms and come back. And the gravitational wave has different effect on these 2 arms. So when they gather together in the receiving part, they form different interference pattern. And in that way, they discover the gravitational waves. Yes, but it takes like, I think 260 million US dollars to build this kind of instrument, and it takes years. For most of the astronomers, they're not so rich. So they really can't build something like that. However, we are thinking, well, but we are receiving light like this. The radio waves are naturally scattered in the sky by different blocks of electrons. And the waves are, the lights are split into 2 paths, and we receive them, and they form interference pattern. That sounds like this is a natural interferometer. And we can take advantage of that if we can really see the interference pattern. However, one step back. It's not that like you put a candle here, you can see the interference pattern. It has to go through the first single slit. because the interference pattern only happens if the initial line are very narrowly beamed. Also, for the LIGO, the input signal, they're using lasers. So this is a demonstration of lasers. Actually, this is lasers as well. So they're very beam signals. So on Earth, you can just easily have that. But in the sky, for example, the sunlight, they're not beam, so the sunlight doesn't interfere. However, pulsar is a different story. Pulsars are beam, as I said before, so that they have the lighthouse effect. Actually, they're one of the most compact objects in the sky. So if you have the light from the pulsar, it is scattered into different paths. And when we receive them, you see the interference pattern. So that is telling you the subtle difference between different paths, and that is telling you the signals you're trying to study in the sky. So we call the study of this kind of interference pattern pulsar simulation, and this is the main focus of our group because we're not so rich, so we cannot build something like LEGO. So we're using pulsar simulation. And another amazing thing is that the separation of these scattered light are greater than the Earth and Sun separation. Those are actually really giant interferometers. So on Earth, yes, you can spend money to build very large interferometers, but it cannot be larger than the Earth. But now we just have something greater than the Earth-Sun separation, and it is built there for you. You just need to study it. You don't have to spend money on it, which is great. And so it gives you extreme resolution of pico-arcsecond. So what can we do with that? We can use it to study the pulsar emission region. This is like last year's paper with former grad student in our group, and a lot of us are co-authoring this paper. So very humiliatingly, although the pulsar is first discovered in radio, but till now we still don't know how the radio lights are emitted on pulsars. We now know that it's neutron stars. We know that how X-rays are emitted, but we don't know how the radio waves are emitted on pulsars. So one of the ways is like you can just use really large telescope to have really great resolution to see really what is happening when the light is emitted. However, because the emission region is so small, we are not usually able to do that. However, with this kind of like giant interferometer of like electron blobs in the skies, we can actually have enough resolution to resolve the size of the emission region and to actually see what is going on when the radio wave is emitted. The only problem is you have to understand the length better, so this is our current focus of the study. Not only this, we can study magnetic field because the pulsar has a wing and sometimes the pulsar is in binary system. The pulsar has strong magnetic field and it is emitting lights, and the companion also has some wings like solar wing, and they crashes each other. So what is happening in between when the magnetic field is greatly disturbed and something like that. So, and so much more, because like previously people think that the scattering of light is some random procedure so that you cannot use it to predict things. However, with current study, we find that the scattering is not so random. So what is going on in the interstellar? What is going on with those weird electron blobs? What are those electron blobs that is actually scattering light? So those are all unanswered questions, and we are all trying to work on that because that is kind of like a trying to understand our instruments better for that procedure. So, in summary, what is pulsars? Although initially it's just like some pulse signals, featureless, and sounds like aliens, But now we actually know that they're fast rotating neutron stars, which is the dead body of some massive stars. And they have very strong magnetic field. They're extremely compact with great pressure, and they pulses in extremely accurate period. And we can use that to probe gravitational waves, and we can use that to facilitate one of the largest natural interferometer in the universe. And I think that's it.
Great, thank you. So we have time for some questions now. And I'll just ask, just because you have a microphone, if you could make sure that you repeat the question. We have time for quite a few questions.
So, I'm kind of curious if you could explain to me a bit more in detail how it is how are you using the period of the pulsar to prove the effects of gravitational waves? Can you explain that to me a bit more?
Okay, yes. You mean this one?
Yeah.
Okay, yes. So, do you know Doppler effect?
Yes.
So, because the orbital motion, so when the pulsar is emitting pulses, sometimes it's moving towards you, sometimes it's moving away from you. And you can see this kind of motion and know their radial velocity because the arrival time of the pulses, so that you know what is the period of this orbital motion. And then you're emitting gravitational waves. So that period is reducing. So the changes in the pulse is telling you the period, and the period reducing can be predicted by the gravitational waves.
Oh, okay. So you're saying that because the orbital period of the pulsars, right, are reducing by say about 75 millionths of a second per year. That is the proof of it. That is the indirect proof of gravitational waves.
Yes.
But how do you not get that confused with the orbital period?
Orbital period?
Yeah, the binary pulsar.
No, I'm talking about orbital period.
I know, but I mean, how do you know? I mean, how do you get the difference of the 75 million out of pulsar by finding those gravitational waves? But how do you not get that confused with the orbital period of itself?
Oh yeah, I see. You mean, I guess you're asking because the pulsar is rotating itself, and it's also orbiting its companion, and you're saying that there's confusion between these two.
Yeah.
Okay.
Exactly.
So when the pulsar is orbiting companions, it's actually a symmetric motion. Especially those are similar masses. So the average period of the whole orbit, spin period of the whole orbit should be the same. And it is tested for this system that the average over a whole period, orbital period, the period of the spin is very stable. So the change, and then you have within one orbital period, there's changes in that pulse arrival time, and that is telling you the orbital motion. And if that is reduced, you can compare the reduction with the prediction from the gravitational waves, and they find that it matches to like 4% or something very greatly. So they think that it's very reliable.
At the very end, you were explaining that there were things about the pulsars that you still didn't know, and you were trying to find out what they were because, and it wasn't, sorry, I didn't quite catch what was the missing information.
Okay, yes. The missing information is, let me pull out the pulsar image. The missing information is, we know that pulsars are emitting And we sort of know that it's like in the direction of poles. But we don't know that at which point is the radio wave emitted. It could be coming from here, here, or here. Yes.
What's a black widow pulsar?
Oh yeah, that's a very great question. Black widow pulsar comes from the black widow spider because the pulsar is eating its companion. So, so you have a pulsar and you have a companion of like I think 0.1 solar mass, a very light mass companion, and the pulsar wing is ablating the companion, and we call that black widow pulsar. And similarly, we also have red bag pulsar. So relatively larger companion, and the pulsar is eating its companion, and that's red bag. So yeah, it's just because it's eating its companion.
I got the impression from one of your slides that by merely examining one pulsar and then detecting a variation in its timing, that in effect would be equivalent to the LIGO. You would actually be detecting gravity waves that might have interrupted the path and changed the timing. Has that actually been done? Or just taking a look at one pulsar?
Sorry, I need to correct one thing. Although I used the demonstration of one pulsars, but actually it's a lot of pulsars.
Okay.
Yes, you're using like pulsar array, like GPS. You need at least 3 pulsars to know where the gravitational wave comes from, and to distinguish gravitational wave from all sorts of noises. And also, the main difference between this pulsar timing array and LIGO is that LIGO are detecting gravitational waves of like star mass black holes. So, and this pulsar timing array is trying to distinguish mergers of supermassive black hole, which is 10 billion solar mass black holes in the center of galaxies. So they're detecting different types of black holes. And it is actively being done like for 20 years. Not yet find it, but yes, it is being.
And it would be detected principally just through tiny variations in the timing.
Yes, exactly. Yes, if it's one pulsar, that could be coming from different things about that pulsar. But if you're using more than one pulsars, there are some characteristic signal you can look for because the gravitational wave passes different pulsars at different times.
You said there was over 2,000 pulsars currently known.
Yes.
So how many of those are actively monitored for their period changes? Do they actively monitor all of them or only a portion?
Oh, that is another great question. Almost all the pulsars, we have measured the changes of the period. However, most of the pulsars are not so stable or not so bright. So I think it's orders of like 20, 30 pulsars that has been used for timing. These are mainly like those stable pulsars because sometimes pulsar has those jitters and itself has some timing noise.
Yeah, they're so faint, they're hard to detect.
Yeah, they're faint or they're unstable. For example, if you're a binary pulsar, you're eating your companion, then you're not stable. So actually monitoring like probably orders of 20, 30 something.
How common is it for a neutron star not to be a pulsar?
Not to be a pulsar. Actually, as for a neutron star to be a pulsar, you have to have 2 conditions. First, it has to emit pulses. Like there are some ways for you to not be able to actually emit light. And for example, very magnetized neutron stars are often like not emitting pulses. Like magnetars are often quiescent. This is one thing. And another thing is the beam has to be offset direction all the time, and that will never reach your line of sight. And also, the beams has to pass across your line of sight for you to be able to see it. So maybe they are pulsars if you see from other planets, but you just don't see it on Earth, so we just don't detect it. So I think a great fraction of neutron stars are not identified as pulsars.
So congratulations on your Nature paper, of course.
It's not mine, but
Your colleagues. I was left thinking, you know, if these results had come a couple of years earlier, maybe we would have got the Nobel Prize because it's detection of gravitational waves. But you mentioned that this is an indirect measurement of gravitational waves. What makes it indirect compared to the LIGO experiment? I mean, it's kind of the same thing, aren't they both direct measurements or indirect measurements?
That's another very good question. The thing is, for LIGO, you see the gravitational waves. But for the binary pulsar, you see the effect of gravitational waves. You don't directly see the gravitational waves, but you see the energy loss due to the gravitational waves.
I see. Yeah, that's it. Okay.
Yes,
yeah, fair enough.
yes.
Cool.
But I think if the pulsar timing array actually see a signal, I think they will want the Nobel Prize.
Yeah.
I think you have.
You explained the gravity wave is like coming from a single point, but out in the galaxy there could be many gravity waves hitting one another. So how do you differentiate this influence of these waves?
That's also a very great question. So, yes, so there are two things they're trying to detect. One is, they call it stochastic gravitational wave background. So if the merger happens far away, and obviously there are much more space far away, so there are lots of merger happening, and it reaches you, and the signals are weak, you don't see it, but you see it background. So that first tells you the merging rate. So it's not, you don't see individual signal from individual events, but you know the rate because of the level of that background. This is one thing. And another is, if you have some nearby sources of merger, because it's nearby, the space are smaller. So then there's not that much events, and also the signal will be much larger than the faraway events. So that you can distinguish the individual events.
So I think we'll just do one more question, although as people are sort of finishing up, Dongzi will be here for a few more minutes. So we'll just take one more from the audience comment.
Where's the energy coming from? Is it depleting the neutron star, or is it accumulating material from around the neutron star? Like to supply the beam?
The beam, yeah, that's mainly the energy of the neutron star itself, because not all pulsars have companions, so mainly their own energy.
So is it going to deplete over time? Will it eventually get weaker and weaker?
Yeah, exactly. So the pulsars are usually spinning slower and slower and slower. So for all the pulsars, we measure the change of their periods, and they're always positive. They're always negative. So it's always spinning down. So yes, it is depleting its own rotational energy. And however, if they have a companion, sometimes you see the spin period is going up because they're eating their companions. They're getting energy from companions. So I think can I ask you?
I accidentally turned the projector off. I meant to. Here you go.
Yeah, I was going to ask, is it normal for those pulsars to have such stable magnetic fields?
Stable magnetic field. Sort of. Well, I don't know how to say stable magnetic fields. You see we call it pulse profile. The pulsar, although you see it's a beam thing, but actually if you zoom in time, it actually have a shape. So that shape can change. So for most of the pulsars. So it's not stable, it's more or less that kind of like dipole-shaped magnetic field.
The period was supposed to be very, very accurate, right? Like the period was like down to like an atomic clock level accuracy.
other pulsars, they're not stable.
Right.
Yes.
Cool.
Thank you.
If I hadn't accidentally just turned the projector off, you would see the link to remind you for where you can find some feedback forms, but it's bit.ly/AstroTours. So again, as a reminder, if you know where you are tonight, you should be able to find the link to fill out this form. We also have some signs around the campus outside the auditorium, but if you want to stand up here and do that, if you show us something at the end after you fill out your Google form, we have some cookies. We of course also have snacks upstairs. But for now, we also have the rest of our activities for the evening. So what is that? We have Planetarium Shows. So if you already have tickets, you'll be meeting at the meet point, which again would be wonderful if you can turn on. But if you head outside towards this direction away from you, there's an elevator lobby, and that is where the meet point for the Planetarium Shows are. If you go up those elevators, that's where you get to the telescope, or Oculus Rift, and so on. And so if you have tickets already for the 9:10 show, our planetarium ambassador, Taylor, will take you over, so be looking for her at the meet point, and also for the 9:10 and 9:50 show. If you have tickets for the 9:30 show, our planetarium ambassador, James, will be taking you over. If you would like to pick up some planetarium tickets, you can also seek out James after I release everyone, and he has a few more planetarium tickets for those shows. I believe it's still cloudy outside, so unfortunately you won't be able to look through the telescopes tonight, but you can head up to the dome and just take a look at our telescope and chat with our volunteers about how telescopes work. Feel free to ask